let's continue with our plan to define more functions and to explore pattern matching further. Let's look at another simple enumeration type that we have already seen, namely Booleans. Booleans are defined as a Haskell data type in much the same way as the choice type that we have just seen. There is somewhere in the Haskell libraries a line that is saying data bool equals false or true. And then it says deriving show, and actually there are many instances for other classes as well in the library. So Booleans support much more than just show, but in particular there is also a show instance. So that means that for Booleans we can do the same thing that we have been doing with the improve function. We can define functions using pattern matching. And actually, even before defining this OR function that is shown here, let's just try to define negation ourselves. So if we try to define negation from bool to bool, that is really very similar in nature to what we've just seen with the improve function. We have to consider two cases, one for false, and there we say true, and one for true, and there we say false. Okay, and now we run into some interesting problem, because not, as we've seen, already existed, and I've just been giving a new definition for it. So what happens if I now call not true? Which definition is used? Is my definition used, or is the one from the prelude used? And the fact is neither. We get an error message when we try to call the function that the reference is ambiguous and that it could refer to either the version I've just written or to the one that is coming from the prelude. And there are multiple ways around this. I'm briefly going to show you these ways, because we are going to re-implement quite a number of library functions in the beginning, right? This is a good exercise in general, and it combines two tasks: the task to get more practice with defining simple functions, useful functions, but also to actually learn the vocabulary of the standard libraries to get an idea of what's provided to you by the library. So we are going to do this a lot. So one option would be to give our function a different name, like my_not. Okay, if I do this, then I no longer have a clash, and I can call my function my_not in much the same way as I can call the original function. They behave in the same way. The other option, and that's the one that we'll typically prefer, is to hide the original version and to give priority to our redefined version. And I can do this by adding an import declaration for the prelude, which I normally do not have to do, because the prelude is magic in the sense that it is implicitly available. But we can still override this magic of being implicitly available by giving an explicit import declaration for the prelude, and then we can modify the way in which the prelude is being imported. And we can in particular use a construct called hiding that allows us to list a number of names, and they have to be listed in sort of between parentheses and separated by commas, that we do not want to see. And I can put the not function here, and if I do this and I still have the not function down here, then my not function is being used, which I can emphasize by making it wrong. If I say not true should be true, I can see that my not function is now being used, even though it has the same name as the prelude one, but we have hidden the prelude version now. Okay, so that is a good way to do this. And similarly, if we want to redefine logical OR, which already exists, so I mean, true or false is an operator in Haskell that will evaluate to true, right? True or true evaluates to true, and so on and so forth. If I want to do this, I also should be hiding the original version now, so that I won't get name clashes if I start re-implementing this. Okay. So how does this work? Well, the OR operator is a function that goes from bool to bool to bool. So it's a curried function that has 2 arguments. And here in a type signature, I actually have to enclose the function name in parentheses because it appears in isolation. And I said that, and basically whenever the function name appears in prefix notation, but also in isolation without its left and its right argument, then we typically have to enclose an operator name in parentheses. The same holds here for the occurrence in the import declaration, actually. Yes. So if I forgot to put the parentheses here, I would get I would get a strange error message. Oh, oops. Some parse error, as we can see. So with not much help as to how to fix it, but right, an operator and for type signature has to be enclosed in parentheses. And then for the definition, now I have a choice whether I want to define in prefix notation, right, or whether I want to use infix notation, something like this. And infix notation, as also for use in expressions, is the more idiomatic thing to do. And now again, I can use pattern matching, right? So rather than putting variables here and giving a definition in terms of other functions, I can make a distinction between multiple cases. And you might think that I need to distinguish 4 cases here, right? So you might think that I could start by making a case distinction on the first argument, and then, well, perhaps I need to make a case distinction on the second argument as well. So I have to ultimately consider true or true, true or false, false or true, or false or false, and answer all 4 of them. And that is easy, I mean, because if you know the truth table for logical OR, then if any of the 2 components is true, then the result is true, right? So that leaves only one case where that is not the case, namely the one where we say false or false, and in that case we actually have false as a result. And so this is a definition that has 4 different cases, and it does work. So this actually is accepted, and it does have the behavior that we more or less want. So this is an option. But it's not the definition that is actually used internally in Haskell. And in fact, we don't actually need to do pattern matching on both arguments. It is usually good to be systematic about pattern matching and to only apply it as a conscious step. And if we go back to the version that we had before, where I said x equals y is something, and now I'm saying, okay, so I should distinguish the case where this is false and this is true, perhaps, right? At this point, we can ask ourselves, perhaps we can already answer these 2 cases now without doing pattern matching on the second argument as well. And if we look at the second case, where the first argument of OR is true, right? Remember that I said logical OR evaluates to true if any of the 2 components is true. So if we know that the first one is true, then the second one doesn't really matter anymore. And in fact, the answer is always going to be true, regardless of what we have chosen for the y here. Okay, so that is something that we can already write down at this point. And for false, that's not possible because it still depends on the y. But let's look at, there are only 2 possible options for y here, right, in this first case. So if the y is true now, then the end result is true. And if the y is false, then the end result is false. So the end result in this case is always equal to y. So this is another option of how to write it, and perhaps I can make it look slightly more nicely by aligning the occurrences of the OR operator. And this still works as before, right? And this is actually the definition that is being used in the libraries. Okay. Let's look at a more interesting type now, and that is our own list type. So lists in Haskell are slightly strange because they are actually supported in a very strong way by the language itself, by giving lists all sorts of special syntax to make them convenient to write. And actually, I think probably from a modern perspective, that is slightly unjustified. In the historical early days, functional programming was all about lists, and lists were the central data structure. And if you look at Lisp as probably being the first programming language that can be called a functional programming language, Lisp was really very literally all about lists, but that carried through many other languages as well. So for that reason, lists have been given preference in many aspects when designing the Haskell language, and they have been assigned all sorts of special syntax. But apart from the special syntax, there are just a normal data type that you could define yourself, and we can in fact define lists ourselves apart from the special syntax. And let's write down another example of a Haskell data type declaration, just to make that clear. So this is becoming a slightly more involved data type definition than the ones that we have seen so far, the one for bool and the one for choice, but not much so. And in fact, many Haskell data types, even interesting data types, are still having very short data type definitions. Right? So what's different here? We are introducing a new data type that is called list. Right now, list as a word, not square brackets. And it has a parameter that is the element type in our case. That is just written here to the left of the equals as well, list A. And there are two so-called constructors. One is called nil, and nil stands for the empty list. Right? And one that is called cons, and cons is deliberately chosen to be called like this colon operator that we've seen before. But this cons is different from all the other constructors we've seen so far in that it has arguments here. So cons takes two arguments, namely an element of type A, a single element, and a list of type A. So that's the list type we're just defining. So it takes an element and a list and it combines them together. It pairs them up, so to speak. Okay, and that, if you remember what we said the type of cons is, the type of cons is a function that takes a single element and then a list of A's, and then it turns into a list of A's. And if we use our own list type and compare that to our new cons function, we see that it just matches this exactly. So our cons constructor takes an A and then a list of A's, but now with our own list type rather than the built-in one, and produces a list of A's. Okay, and nil is of type list of A and corresponds to the empty list, which normally has the special syntax that it can be written as square brackets where square bracket closed, and then has this type. But if you look past the syntax, then we have exactly the same structure. And in fact, we can build lists now with these two things, if we have these two functions, by repeatedly applying cons and then using a final nil in order to add elements into a list. So how would we build a list that has like three numbers as integers? So let's say we have a list of int. How do we do that? Well, we can start by using cons and then use 1 as the first element, and then the rest here should still be a list. But there we can use cons again and say we have 2 as the second element, and then the rest should still be a list. But there we can use cons again and have 3 as the element, and then the rest should still be a list. And there, because we don't want to have any further elements, we can use nil, and then complete the list. Now we should also write deriving show here, so that we have a hope of showing these values. So if I do this, then I see that this value sample list evaluates to itself. Cons 1, cons 2, cons 3, cons nil. Constructors never evaluate to anything. They always evaluate to themselves. They determine the shape of the data. So the cons constructor defines a shape of a list that is not empty and has a known first element and then has a tail that is another list. Now you could say that is a whole lot more complicated than what I'm getting if I'm actually doing 1, cons 2, cons 3, cons the empty list. Namely this nice syntax, square bracket 1, 2, 3. But in fact, even for the say predefined lists with the special syntax, this shape with the cons and the nil applications is actually the one that corresponds to the internal representation. This is actually the way that lists look like internally in Haskell, and this is just a nicer syntax. Right, so lists in Haskell are not arrays. Lists in Haskell are linked lists, and you can think of the cons as essentially being a little node in memory with a pointer to the first element and with a pointer to the rest of the list. And that is the structure that lists are really expressing. And the square bracket comma notation is just there for convenience. Of course, it's much more convenient to look at, but as far as the internal structure is concerned, our list type is equally good, right? It has exactly the same structural representation as the built-in one. So we have kind of faithfully reproduced the list data type in Haskell. We could just not reproduce it with the built-in syntax. We can actually, and that is a good opportunity to briefly interject, we can actually use a GHCi command that is very useful, :I for info, to get all sorts of information about various different kinds of entities in Haskell. And we can use that to get at the definitions of types. So if we call :I with bool, we get a lot of output. But let's look at it. So the first line is a bit strange, so let's just ignore this. This is a so-called kind signature. We won't need this for the time being, and it's optional anyway. The second thing, the second line, is the data definition of bool, and that is exactly the data definition that I have been showing on the slides. Right? If we go back here, that is exactly this: data bool equals false or true. Right? And then subsequently, it also lists all the instances for bool that are in scope. It doesn't show details about them, but it does show you that bool is an instance of the EQ, of the OR, the enum, the show, and the read, and the bounded class. And in particular, it's an instance of the show class. Right? So we can type true and get true printed back. Okay. And we can do the same with our own data type that we just defined. So if we do this with choice, right, you can see that you get data choice equals rock, paper, scissors from your own module. And you see that it is an instance of the show class. You can ignore the safe annotation here. That does not play a role for anything that we're currently doing. It also shows you, as you can see here, where these data types are originally defined. So it shows you that this data type bool is originally coming from a module called GHCtypes, which lives deep in the internals of GHC itself, but it is then propagated to the prelude and coming into scope via the prelude. Okay. Now, if we can actually do this for the list type as well, but you have to know how. So the magic incantation for the list type is you have to use this. Let's just square bracket open, square bracket close. And then you get a definition that you could not have written yourself because of the special syntax, because these square brackets are simply not allowed as a syntax for your own data types. But it shows you that the list type is a parameterized type as well, and then you can actually write list of integers in this way, like square bracket open, square bracket close, space int, but typically it's then also written square brackets surrounding int as a type for list of integers. So this means that the list type is parameterized just like our list type is, right? And then it has one constructor, nil, which is having this special syntax, and it has another constructor which is written in infix form because it is symbolic, and it is written between its two arguments, the first one being of type A and the second one being of type list of A. Okay? Good. Okay. So now that we have seen how to define the list type, we can actually also define functions on the list type by means of pattern matching. Okay? Before we do that, let me briefly mention this one extra aspect here. We'll sooner or later get into situations where we have to talk about the priority of operators. And so if we can define our own operators, such as OR here, or just as cons for the constructor for lists, we have to talk about, like, if we introduce a new operator, how does it behave with respect to other operators? We have certain expectations in some domains. So, for example, we typically expect that multiplication binds stronger than addition, so that if we write something like 3 plus 2 times 7, that 2 times 7 is evaluated first to 14, and then we get 14 plus 3 is 17. And that is indeed what we get, and not that 3 plus 2 is evaluated first to 5, and then we would get 5 times 7 to 35. So in this case, we would have to put parentheses around 3 plus 2 if we wanted to have that interpretation. How do we know that plus is weaker than times? That is governed by these so-called infix declarations that can be given for operators, and we can use the info command also with an operator name. We then get information here that is currently irrelevant for us, that plus is actually defined within the num type class. But in particular, we get this line here, which says that plus is an infix operator that is left associative. So that's not really important for plus, but it means that if we have multiple occurrences of plus, they will be implicitly grouped to the left, okay, and that it has priority 6, and 6 is just a number that ranges from 0, I think, is the lowest, to 9 or 10 is the highest, and the higher the stronger it binds. So we can compare this to times, and we see that times is infix L7, so times has a higher priority. And we can do this for logical operators as well. We'll see that and the logical and has priority 3 and is right associative by default. And now the OR operator, that's the one that we've defined. We have not given an infix declaration for it, but we should get some default priority, but that is very confusing to work with the default priority. So we should give it a priority, and I think the one that is defined in the standard library for it is 4 and also right associative. And so we can just add this as an additional declaration. And similarly for the cons operator that appears as the constructor in lists, we also have a priority 5, and we also have that it is right associative. And for cons, it is really useful for it to be right associative, because I've already said if we wanted to write the list 1, 2, 3 in our list notation, it would normally look like this. But now, because it is right associative, we can at least drop all the parentheses and it still means the same. And also the type of cons makes it so that the left associative interpretation is usually not useful, because this isn't even type correct. We are trying to cons two numbers on top of each other, but the right argument of cons has to be a list, so we get a type error here again. Okay. Okay, so now let's try to define a function by means of pattern matching on lists. And let's try to do this with a function that checks whether something is an element in a list, and a particular value, you can think of it as a number, is an element in a list, occurs in a list. Okay, so we have two arguments here. We have x and a list. We can call that access, and we can use pattern matching on the list. Right, and I can actually do this for both my list type or for the built-in list type. We can do this for both in sequence. So let's first do this for our own list data type. So then my case for the empty list is for nil, and I have to write something here. And my case for cons, now this is new because the cons constructor has arguments. So when pattern matching on cons, I have to give names to the argument. So I can call the first element of this list y and the rest of this list ys. And I have to give a definition here as well. Okay. And lm is actually a function that also exists, so I should also hide it from the prelude. Okay. So now, if I look for an element in an empty list, then it's never contained, and the empty list does not contain any elements. So if our element check is supposed to produce a Boolean result, then the Boolean, in the case that the list is empty, that comes out of it is always going to be false. Okay? And the case for the non-empty list is a little bit trickier, right? Because if you think about it, you have a list that starts with y, and it has a rest of the list ys. Now, okay, so one thing that's certainly interesting is to see whether x is equal to y, okay? Because if x is equal to y, then x is certainly contained in that list. Right? So I could write x is equal to y. So how do we check whether something is equal to something else? It's a function that we haven't actually seen yet, that is provided by an operator called equals equals. Right? So 3 equals 5 is false, but 4 equals 4 is true. And the same thing also works for all sorts of other things, for Booleans themselves or for character literals. And in fact, the type of this equals equals operator has an EQ class constraint, so it works for a whole lot of different types. Okay, so we could check x equals 4 here. Okay, and we see that type inference actually infers the type for us that we should actually have been written up front, and we'll do so again in the future. But we see that it actually, I wanted to show this, correctly infers the most general type here. So it does not say suddenly that lm needs to take an integer and a list of integers or something, but it actually says lm needs to take an a and a list of a's, so a compatible list, and the a has to support equality because we're using the equality test here. Now at this point our definition of lm type checks and can be used, but it is not correct. Right? Because if we check whether, let's say, 2 is contained in the empty list, then we get false. And if we check whether 2 is contained in the list 2, 3, then we get true. But if we check whether lm2 in the list cons 1, 2, 3, right, then we get false, because at the moment we only ever check whether the element we're looking for is the first element, and we're completely ignoring ys. But we also have to check whether x is an element in ys. And, well, what can we do? We can use recursion, because ys is a shorter list, and we are defining our function right now. We could just use recursion to check whether x is contained in ys. So now if we also perform a check here whether x is contained in ys, then we only have to think about how do we combine these two results, if we know that x is equal to y or not, and if we know that whether lm x in ys in the tail of the list or not, how do we combine these two Boolean results? And the answer here is just that this is an application of the OR operator, just as we have seen the OR operator before. So I'm getting a type error here. So this is an interesting one. So I probably made a mistake with the OR. Yes, okay. So no, OR should actually bind weaker than AND, right? AND is more like multiplication, and OR is more like addition in certain ways. So I made a mistake there. I should have defined the priority of OR to be weaker. Otherwise, we have OR and equal being at the same priority, and we're getting an ambiguity between these two errors, which could be resolved by putting explicit parentheses here, which is like, this is one of the cases where I think explicit parentheses can help make something clearer. So we can leave them in, but in particular, if we now leave them off because the priority of equals is 4 and the priority of OR is 2, this type checks. Okay. And now if I make this check, it also correctly says true. And only if I actually look for something that is really not contained in this list, I do get false. Okay. And I could do exactly the same with the built-in list type. So let me actually perhaps keep this one around, make a copy. Rename this function here to lm prime. So the prime character is just a valid identifier, a part of an identifier. I can add this without, like, it has no special meaning, but lm prime is just a different function now than lm. And now I can change this here to the built-in list type, and then I have to change the pattern for nil to the this notation, and I have to change the pattern for cons to ycons ys, and the rest is exactly the same. And now I can use lm to 1, 2, 3 with this notation, right? lm 0 and 1, 2, 3 is false. Okay. Note that pattern matching always follows a common structure, right? So typically we have as many cases, naturally, as there are constructors for the data types. The improve function had 3 cases because choice had 3 constructors. The not and the or function had 2 choices because the bool data type has 2 options. The lm function has also 2 choices because the list data type, both the predefined one and our own one, have 2 shapes, right? Nil and cons. We have 1 case for each. There is an additional thing that is coming into play here for lists, because lists are defined recursively. The cons constructor refers to the type that we are just about to define. And that means that functions are also functions over lists are also naturally recursive, and we'll see that a lot, that functions follow the shape of the data types. Most functions over lists will be recursive. Recursion in Haskell is ubiquitous. It is not something to be afraid of. I know that in some other programming languages, you get taught that recursion is something to be avoided because it's inefficient and it leads to stack overflows or something like that. In Haskell, this is not something to be afraid of. Recursion is the way to do anything useful, essentially. And we'll talk more about the efficiency aspects later. But it is there is basically no other way to do anything, and also you don't easily get stack overflows. Okay. So this is being done here on the slides as well. It is perhaps a good idea to briefly talk about how to think about Haskell's evaluation. Like how to, in your mind, how to conceptually think about, if you have a particular function call, what is actually going on behind the scenes. And there is a process that is very systematic and that we're going to use many times throughout this course that is called equational reasoning, and I want to show you an example on how to do this. and that will also reveal one other aspect about Haskell to us that is slightly special, and that is that Haskell is using lazy evaluation. But I'm going to do this in the next video.